Hello, I'm Zhao, and this is our paper named Exploring Dominant Path in CTC-Like ASR Models, Unraveling the Effectiveness of Viterbi Decoding. This is also a co-work with Peter Bell and Ondřej Klejch at the Center for Speech Technology Research, the University of Edinburgh. We will first go through the introduction and briefly have a look at what this paper is about. After that, I will introduce the method that we apply in this paper, where we will introduce two lattice-based metrics for evaluation. Then we will introduce the experiment settings and have a look at the results. Finally, we make the conclusion, which will also include the weakness that we believe this paper has. So first, let's have a look at why we wrote this paper and what questions this paper is trying to answer. First, is there a dominant path in the decoding space of a CTC or a CTC-like model? Some people may believe that a dominant path does exist in the decoding space, as sometimes we can even achieve a very good WR performance with a CTC model, even by a greedy search decoder. However, we should investigate whether this is true or not. If that's not the case, the second question will be why the Viterbi decoder or greedy search can still work fine with CTC models. The last question is that with a differentiable WST-based framework, we can change or modify the topology with almost no limitations. So we may wonder whether changing the topology can make a difference. Here's how we did it. In order to answer the aforementioned questions, we'll see two proposed lattice-based metrics with which we can see the proportion of the best alignment in the lattice and the proportion of the best hypothesis in the lattice. To change the topology flexibly, we also apply differentiable diversity-based end-to-end ASR framework, which we will see in the next section. To briefly let you know about what we found, just in case you are not patient enough to watch the whole video, we found that there's no dominant path in the decoding space, regardless of the topology choice. Besides, the Viterbi decoder remains reliable as long as the best hypothesis occupies more than half of the probability in the lattice. If you're interested in how we found this, just keep watching. Here are several FSTs that we're going to use for training and decoding. First, the imaging FST is transformed from neural networks upwards. Second, the lexicon FST, which is the same as the lexicon FST in Kaldi, and you are probably quite familiar with that. The third one is the token FST, and the concept of topology we discuss in this paper is exactly the topology of the token FST. Next, the linear word FST, which is transformed from the transcription Y. Finally, the grammar FST, G, which is usually derived from an n-gram language model. So this is the objective function for training. If you are familiar with CTC, you will find that the numerator part is quite similar to the definition of CTC loss function. However, it also has a denominator part. Actually, CTC is a special case in this framework, where the denominator is always 1. But for most other topologies, the denominator is not always 1, so the denominator has to be computed during training. If you're not familiar with this framework, I would recommend you to read our previous paper published in Interspeed 2023 and another paper about differentiable diversity published in 2020, as shown in the footnote. Then, let's have a look at how to calculate the objectives, namely the numerator and the denominator, with differentiable WFST. First, to calculate the numerator, we construct the training graph as shown in the second equation, which is a composition of T, L, and W. And of course, there are several graph optimization operations involved here in the real implementation, but for simplicity, they're not mentioned here. With the training graph in hand, which works as a filter that only keeps the path corresponding to the transcription, we can then compose E with it and calculate the total score of the resulting FST, which is exactly the numerator for the denominator, as it is impossible to calculate for all possible word sequences. We approximate it by composing E with T, and computing the total score. In this way, we only take valid paths which are acceptable by the token FST into account. As for the decoding, we first construct the decoding graph as shown in the first equation. When it comes to decoding method, there are two basic types of strategies. The first one is called Viterbi decoding, where, as we can see here, the probability of the best alignment is taken as the probability for the hypothesis. On the other hand, the second one, full-sum decoding, takes the sum of the probabilities of all the alignments corresponding to the hypothesis as the probability for the hypothesis. Remember that during training, we had to choose the full-sum style as there's usually no alignment information readily available. However, it seems that in most cases, the WI performance with a Viterbi decoder is already good enough, implying that there might be a dominant path in the decoding space, even though we applied a full-sum style during the training phase. We will have a look at this in detail later. Now we introduce two lattice-based metrics, best path proportion and best hypothesis proportion. Given a lattice, we can easily compute these two metrics as the definition. First, best path proportion calculates how much the best alignment occupies among all other alignments corresponding to the same hypothesis, W star, and W star here denotes the best hypothesis chosen by the Viterbi decoder. The larger BPP is, the more probably we believe there is no dominant path in the decoding space. On the other hand, BHP represents how much the best hypothesis, W star, occupies in the whole lattice. An interesting fact is that if the value is larger than a half, 0.5, that indicates the decoding results of a Viterbi decoder are the same as a full-sum decoder on this lattice. We will see how this matrix works later. So here are some basic settings of our experiments. We first fine-tune Web2Vec 2.0 models, basically Web2Vec large LV60K on WSJ and LibreSpeech with various topologies. And then we apply phoneme as the modeling unit. The Viterbi decoder, decode faster, is applied for decoding in Calzi. And K2, we use it as a differentiable WSD backend here. So here are 8 topologies that we explore in this paper. They are named in an SXTY manner. So XXTY means that there are X states for each phone, and the minimum traversal frame is Y. And one more star means there's one more self-loop added. We deliberately choose as many topologies as we can, just to have a thorough exploration. So first, let's have a look at the overall WR results. So we can see that for WSJ, all the topologies have relatively similar results. On LibreSpeech, most topologies have a WR around 8 or 9, but the last two have quite worst performance due to bad convergence. We would like to show the WR results to make sure that the most of the end-to-end ASR system here are working pretty well. Then let's have a look at best path proportion on WSJ and LibreSpeech. We can see that there's no dominant path in the decoding lattice, as the maximum value of BPP is still smaller than 1%. Remember that the denominator is the probability sum of all the paths corresponding to the best hypothesis. And if we change the denominator to be the whole decoding space, the proportion will be even smaller. We have seen that there's no dominant path in the decoding space, so why can Viterbi decoder still be reliable? The results of the best hypothesis proportion can answer this. Recalling that if P hypo is larger than a half, then the Viterbi decoding is equivalent to a full-sum decoding on the lattice. We can see that on WSJ, where all the models perform quite well, all of them have a quite high ratio of P hypo larger than 0.5. However, on LibreSpeech, where the WR is a bit worse than that on WSJ, the ratios are smaller, especially for S3T2 star and S3T2 double star, which did not converge very well. To further investigate BHP, we split the WSJ evaluation set into two parts. The first one only contains the utterances which got a high p hypo larger than a half, and the other contains the opposite only. We found that the WR performance on the first subset is significantly better than the second one, which confirms our explanation. So let's have a short conclusion. We first have a look at the reliability of the Viterbi decoding. The study investigates the reliability of the Viterbi decoding CTC-Like end-to-end ASR systems across different topologies. And then we have a look at the lattice, and we do some lattice analysis, and the analysis shows that a dominant path in the Viterbi determined hypothesis often does not exist. Yet decoding remains reliable when the hypothesis accounts for over half of the lattice. And then we do some comparison with CTC. We do some comparison among all other topologies with CTC topology, and we found that CTC topology underperforms in terms of word error rate and robustness when using the Viterbi decoder compared to other topologies. So I always believe that it would be better for every researcher discussing their paper's weakness themselves. I think the main weakness of our paper here is that we did not include the WR results of a four-sum decoder due to an implementation issue. I believe that we will include that part in the future. And so finally, thanks for watching, and if you're interested in this work, please scan the QR code here for the paper and the code.